Hello guys, we are gonna discuss today about practical AI with machine learning for observability, especially how it is implemented on the data. You know, machine learning in observability has been criticized a lot over the past years. And there is also a presentation from, let me show you, from Google, where actually Google 19, they said that machine learning and observability will not work. But if you read carefully, what they say is that our expectations from machine learning in observability are wrong. It's not observability, it's not machine learning itself that is problematic. It's what we expect it to do. Now, in a data, we have a long history with machine learning. We started in 2020. And we have developed, the data is a distributed platform. So you install it, you install agents all over the place. And these agents are smart. They are a complete observability pipeline behind the scenes. And then when you want to view your entire infrastructure, all these agents become a distributed database. So instead of pushing the data, centralizing all the data to central databases, the data remain at the edge, and we distribute the code that is smarter this time, and it has machine learning in it. So it learns the behavior of our infrastructure directly at the edge. This is what we're going to say today. So machine AI in general has become a lot smarter these days. And most of the observability platforms offer some kind of AI. I'm going to show you what is the hardest question, let's say, that you can ask an AI assistant today that is connected with some observability platform. And this question is this. It's very simple. It's, hey AI, how is my infrastructure today? Now look why this is hard. This is hard mainly because observability data are vast. Hundreds of thousands of metrics, millions in most of the cases, especially in a data case that we collect almost everything, it's many millions. And as the infrastructure grows, the data available to query are extreme. So how an AI will think, how an AI will accept this question and think. So this is a typical plan. This is what they are going to do. The first is that they're going to get the raised alerts. Okay, let's see if you have alerts and if the alerts say something about your health, the health of your infrastructure. Then they will query a few, the most critical nodes as they find it from the list of nodes, the most critical nodes by CPU, memory, and disk pressure. The last is that they're going to get a few logs, not a lot, mainly because the context window in the memory these AI agents have is limited. They are going to get the last few entries to see if they find something interesting. Only if you are lucky, they will attempt to discover some metrics about errors or latency. So they are going to do some kind of metrics discovery to understand if there is something interesting in there, and then conclude. This means that it's luck. It's not predictable what it's going to happen. They may say to you that your infrastructure is everything fine, but you may have significant problems, and the opposite. And this happens because they lack context, so they don't know what is happening. Now, in a data, mainly because we have this machine learning that runs at the edge, we have added to the tools, let's say, that AI assistants have, a few very interesting functions, calls. These are the find anomalous metrics. So given a time, all these tools demand from the AI assistant to know only the time frame. So I'm interested to know from that time to that time what happens. So these tools, the first tool, the find anomalous metrics, returns scores all the metrics according to their anomaly rate, and returns an ordered list of the most anomalous metrics among all of them. Correlated metrics and unstable metrics, they work on the pattern. So they try to find the same scoring engine, but this time it examines 2 time periods to actually decide if the metric changed significantly or it is unstable. It was stable, it's now unstable. These tools, combined of course with all the observability tools that all platforms have, allowed Nedata to offer these services. So on Nedata dashboards, you are going to find Ask AI next to any alert. This performs root cause analysis on the alert to find why it's raised, what's wrong. AI troubleshooting. This is a button that exists all over the dashboard. So on any screen, it's actually a global item, a global button on all dashboards. And what it does is that it captures the context of what you are seeing in front of you. It may be logs, it may be alerts, it may be charts, metrics, whatever, and tries to analyze what's happening there. We have AI insights. This generates professional reports. This may be post-mortem analysis, blast radius detection, performance, availability, capacity planning, generally any kind of report that you may need. And AI chat, where you connect any data actually to your Claude or Codex or ChatGPT or whatever, and you can start asking questions, interacting with the data live. Now, how we designed ML, the biggest differentiator, this is also the presentation, is about machine learning. Okay? So what we did about machine learning in the data. So the data, as I said, is a distributed platform. So you install the agents all over the place. The agents are lightweight. Actually, the goal is to collect, they have auto discovery of metrics, and they collect as much information as they can find. Usually this means 3,000 to 20,000 metrics, unique time series per server. All of them collected per second. Nedata is the only true real-time monitoring system. All the others are, at the best case, near real-time, 10, 15 seconds, or not real-time at all, per minute, etc. Although most say that they are real-time. But anyway, so the goal of this was to detect anomalies automatically, without manual configuration and without any training required. So the system, to ship an algorithm, a system that automatically learns the patterns of our infrastructure. This system to be extremely lightweight. So at worst case, to get 5% CPU utilization of a single core. So something that is lightweight to be always there. And of course, not to have any significant memory impact. So what we did is that we used the k-means algorithm. This is a clustering algorithm, machine learning. We train 18 machine learning models per metric. That's a lot. So if you have 10,000 metrics on a server, you have 180,000 models. Why 18? The key thing is that we wanted to be rolling, so to forget the past. This is unsupervised, so you don't instruct it, you don't say to it what is good and what is bad. It detects anomalies by itself. So the crucial part is to forget. An anomaly happened today, it has to forget it after some time. So in order to achieve that, we train 18 machine learning models at different time frames. So we will see in the next slide, we train every 3 hours, 6 hours of data. But what we did there, mainly because machine learning is noisy. So if you do this with one model, you are going to have some false positives. So what we implemented is a consensus mechanism. So all models need to agree in order for a sample we just collected to be flagged as anomalous. Now let's see a little bit how this works. As I said, every 3 hours, 6 hours of data. This is overlapping. So the two models, any two models overlap. The second thing is that we are not interested about the actual value of the metric. So let's assume that we have a speedometer on a car. It shows 50, 60, 40, 70, whatever the speed is. We're not interested about that. What we learn is how the car accelerates or decelerates. So we're doing the delta. This is the difference and smoothed 5 lags. So we're trying to understand how you drive it. Are you aggressive? Are you not aggressive? How you drive the car. And once we learn how you drive the car, then we can say if a certain moment of your driving is an outlier or not. You're not driving like that usually. So this is what happens. We train for every metric. It may be CPU utilization, memory, it may be database request per second, web server latency. It doesn't matter. What we try to understand is how these metrics fluctuate, how they get increased or decreased all the time. What happens there? Once we learn this, we learn 6 hours of data on your data. It's not trained somewhere else. It's trained on your machines. Once we train this, we keep 18 such models. Now, in order for us, for each model to say that something is anomalous, it's this equation below. It's not that important. What is important is that anomaly detection happens in real time. The biggest problem that most monitoring solutions that advertise machine learning have is that they are influenced from the events after the fact. This is not. The data is not influenced at all, mainly because this is computed the moment we collect a sample and we persist it to disk. So there is no way for us to influence that after the fact. It's real time, as it happens. Now, this is how the consensus that we have, this is how it works. It's a summary, so we have in total 2.4 hours, days of memory, let's say, 57 hours. And all 18 models need to achieve consensus, must agree, in order for us to mark a collected sample as anomalous. Now, the interesting part is the overall anomaly rate. As I said, each model has some small error rate. Each model has a small error rate. Theoretically, it's 1%. What happens now is that mainly because of this consensus of 18 models, the anomaly, the false positive rate, the theoretical false positive rate of net data is this tiny number with a ton of zeros. You see, it's a really impossible number. Of course, there are some false positives in real life, but the whole point is that the theoretical model behind these calculations is such that they are extremely rare. Now, one of the things that is important is that we went a level further. So we have per metric now 18 machine learning models, very good false positive rate, anomaly detection that works on the servers themselves and on your data, not on some lab or some sample data, on the live data that are collected. What we did then, what we noticed is that when we had all these anomalies we had some issues, we noticed that anomalies happen in clusters. So it's not one metric that becomes anomalous. It's a lot of metrics that become anomalous at the same time. So there is a clustering there. And we defined in the data host level anomalies. So the host level anomalies, if a server has, I don't know, 3,000 metrics, we say that we need at least 1% of them to be anomalous. So 30 metrics to be anomalous concurrently, in order to mark a host level anomaly. This eliminates the noise, even this tiny impossible false positive rate eliminates the noise completely. Because now it's the probability, as you see, is 10 to the minus 1050. This is a lot of zeros after the dot. Now, this is how it looks. So this chart, the first chart you see on the top, shows the percentage of metrics that are anomalous per node. The dimensions, the lines are nodes, and the spikes you see is which nodes had what percentage of anomaly together. You see that the chart here is at 5%. And these are the host level anomalies, the individual metric anomalies as a percentage per node. This is the absolute number of metrics, while this is percentage of metrics over the total of a node. This is the absolute number of metrics, thousands of metrics. You see 2,000 metrics became anomalous together, concurrently, same second. And here are the last chart is the host level anomalies that Nedata marked. This is how the data works. This is a pipeline inside each Nedata agent. So as you can see, Nedata discovers metrics, collects, detects anomalies, then stores in the database. After storing in the database, we have all the different other stuff like alerts, alert transitions, scoring engine that we said at the beginning, MCP servers for you to connect AI assistants, streaming to create parent-child relationships between the data, exporting if you want to export data to Prometheus or Influx or whatever. And of course, we have machine learning training. So machine learning training is a separate path inside the data. Now, how we managed to reduce CPU. This sounds machine learning on every metric and thousands of metrics collected every zero. Training all these metrics, all these models would require significant effort. So how we managed to settle and balance the consumption, let's say, that machine learning has, the effect that it has on resource consumption. The first is that many metrics are usually zero. So this may be hardware errors or exceptions. These are usually zero, and usually there is also an alert there that says if this is not zero anymore, raise the alert. So we excluded all of them. Then we have a lot of metrics that are usually constant. It's the pool size of the connections of a database server or the total memory of the system. So these are totally constant for their lifetime. We excluded this too. Then what we did for the rest is that we have 3 hours to train them all. If your server has 10,000 metrics or 3,000 metrics or whatever, we have 3 hours to train one model for each metric. Now, what we do there is that we throttle. We spread the computation over time so that you will not see a spike of computing models, but every second, just a few will be trained. Now, this usually in most installations of Nedata, this results to 1 to 4 metrics training per second. This is nothing. This is ignorable for the k-means algorithm. So this is how we manage to have a small, ignorable resource consumption. Now, the memory footprint, we need 18 kilobytes per model. So the anomaly bit is stored in the database. So the moment we collect it, we put it in the database. What is the storage overhead of machine learning? Zero. Why? Because we have developed a special, a custom floating point number where all the samples are stored in the data. And we put the anomaly bit, if a sample is anomalous or not, after the 18 models have reached consensus, we write it as a bit in that number. So even if you disable ML, the number is going to be still there. So we're not going to write less bits. This makes the overhead, the storage overhead of machine learning, zero. Now, what machine learning can detect? Of course, since we learn the rate that numbers change over time, we can detect spikes and dives. Spikes and dives that are sudden. This happened. It never went from that number to that number before. We can detect that something is missing. So when this thing happens, the next would be, this is a seasonality, the next would be to have the seasonality repeat itself. So in this case, it's missing. We can detect strange dives. So something, a number a metric that fluctuates at a certain level, suddenly drops to a new level. We can detect that something has a trend that drifts, a slow and steady drift over time, like a memory leak. And of course, some strange steps. So all these are what the machine learning can detect on every metric. Now, what it cannot do, it's not magic bullet, it cannot do everything. So short-lived workloads. When machine learning needs time in order to train models and actually build the models in order to detect anomalies. For very short-lived workloads, CI/CD workloads, machine learning will not do. So it doesn't have the time to train models on CI/CD jobs. Crash services. So machine learning needs metrics in order to detect something. What happens if something crashed? It's not there anymore. No metrics. So how machine learning will detect anything? Since there is no sample collected at all. So what happens in this case, and this is the amazing thing about machine learning, is that this crash on this server will have a blast radius. It will affect a lot of other services that depend on it. So, and the others do not crash. So all the others will suddenly go anomalous. So in this case, machine learning cannot detect the root cause, but it can point in the right direction. That all these are anomalous and there is the problem. Whatever is the dependency of all these, this is the problem. Slow degradation below a radar. So I said that it learns how metrics change state, how metrics behave. The key issue here is that if something is extremely slow, it happens at a very, 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 very small rate, over probably weeks, it will not detect. So this will detect more sudden, more immediate changes. Constant metrics that suddenly change, yes. So mainly because we don't train machine learning for them. For all these, the obvious solution is to have alerts. And of course, it learns anomalies too. So if an anomaly happens now, it will not be anomaly in an hour or in 2 hours. It needs 2 days in order to forget it. So for 2 days, the same anomaly that is flagged and detected now will not be anomaly anymore. Now, machine learning, in order to understand the work that we have done in the data, we have integrated it everywhere. So the data is AI first and machine learning first. Uh, Now, this is in a data chart, a normal chart, like all charts. What is different about it? So there are a few things that are different. The first thing is that there is an anomaly ribbon. Where's my mouse? Here. There is an anomaly ribbon. This anomaly ribbon shows how many anomalies, how intense is the anomaly rate inside on these metrics that are visualized. In this case, we are seeing 115 applications over 7 nodes, eh? 2 dimensions. This is context switches, so it's volatile, not non-volatile probably. 2 dimensions and a lot of labels. Now, this ribbon, the anomaly ribbon, shows at this time how many anomalies there were across all applications. Now, we call this menu the needle framework. This menu that is on the top, we call it needle, node instances, dimensions, and labels. What this allows is to pivot the chart in any way you see fit. The observability data are like a cube. You can see them in different ways. So what this little menu does there is eliminates completely the query language. So in the data, you don't need to learn a query language. Everything is point and click. And with this little menu there, of course, we have done a lot of work to be that minimal. You have filtering for everything. So you can filter any dimension, any instance, any node, anything, any label. You have the ability to regroup the chart, group it by application, group it by node, group it by label. Actually, you have the ability to do it in 2 levels. So double grouping like that and then like that. Now, there is also an info ribbon. The info ribbon below shows you issues, errors, whatever, missing samples, partial samples, counters overflown. So stuff that you should know in order to trust the data that you see. Now, let's go and see what happens inside. Inside each of them, so you see here, it's the nodes drop down. You click here, you get this. Anomaly rate is analyzed per node. So you can see on the chart anomaly rate over time across the entire thing. And on the nodes tab, on the nodes drop down, you can see the anomaly rate per node. Together with minimum, average, maximum, you see number of metrics, instances, volume contribution of the chart. So 16% of this chart comes from Bangalore. Similarly, you have the same logic, the same methodology on applications. Again, you see that SSH or whatever on the SSH here, VPNs or whatever, there are just a bunch of applications listed. These applications, again, are scored with anomaly rate. Per label, so you can see for every label, it's anomaly rate. Nedata does all these calculations in one go. So you ask for a chart, and in one go, Nedata returns all aspects of the cube. Of course, the time series is about what you asked, the grouping that you want, but all the other aspects that could be useful for you are analyzed in one go. This methodology allows Nedata allows every chart of Nedata to be a complete analytical tool. You can immediately spot who is the offender, where are the anomalies are, where the volume of the chart comes. So all this with one go. It's like 20 or 30 charts of other observability solutions. The same anomaly rate appears when you hover the chart. So this is a hover, a point, anomaly rates on that point. And we said about the scoring engine. The scoring engine is what allows the AI assistants to ask Nedata to score a lot metrics, all the metrics actually, against an algorithm. To say, for example, what changed over time, what is more anomalous at this time frame, etc. So The scoring engine is a unique feature of Netdata. No other monitoring systems have it. They don't have it because it's extremely expensive to have it, mainly because Netdata is distributed. So we have scoring engines all over the place, and the work that each one has to do, it's tiny, it's small. So what we can do is ask all the agents to actually score according to a fixed algorithm their own metrics, and then we get them back, we aggregate the list, and we present it to you across the infrastructure. Now, the metrics correlation, so to find relations between metrics, is a subset of the scoring engine. There are a few algorithms there that are used especially for that purpose. So on a data chart, the first thing that you can do is can ask, what is interesting now? So you have this AR button here, which once you click it, the data scores. These are sections on the dashboard. These are dynamic. And the data dashboards, I forgot to tell you, are totally algorithmic. So you don't design the dashboards by hand. The system by itself designs all the dashboards. So it's an algorithm that is driven by metadata. We annotate all the metrics with some metadata, and then we have an algorithm that is the dashboarder, creates dashboards. Of course, you can create custom dashboards if you want, but even these are just drag and drop, point and click. AR button, the anomaly button, once you press it, it calls the scoring engine and tells you per category where are the anomalies for the visible time frame. So you change the time frame of from the datetime picker, you click the anomaly button, boom, this is interesting now. This is the anomaly advisor. We saw it before. I will not go again. It's the same logic. You see here the first case it shows the cascading events of anomalies across nodes. Every line is a node, and you see how the nodes went anomalies one after another. On the second anomaly, they happen concurrently, and you see actually that the big spike of anomalies is a little bit later. It's not together with the others. In this view, the anomaly advisor view, when you highlight an area, any area, it doesn't matter, Netdata will give you an ordered list of all the metrics that weren't anomalous in this time frame, scored, ordered by anomaly rate, how intense the anomaly was. This allows you to have root cause analysis. It's very easy, for example, and I do this with Netdata customers all the time, where they have a problem and I happen to be there, and I say, okay, well, guys, it's very simple. We go to the anomaly advisor, we highlight the spike or the dive or whatever is interesting there for the customer. We press a button, we get an ordered list of all metrics that are related to that thing, that were mostly anomalous during that time. And immediately within the first 10, 20, 30 results, you can find the root cause. It may be a backup started or a user logged in or some administrative work in most of the cases, and of course crashes or whatever else. So what's the highlights? Machine learning at the edge, unsupervised. You don't need to do anything about it. It just works for all metrics, thousands of metrics per second, true real time for all metrics, available everywhere, on every dashboard, on every chart. There is a scoring engine to help you find the needle in the haystack, root cause analysis, blast residue detection, all this. So Netdata is one of the most popular observability projects on GitHub. Actually, it's the most popular in terms of stars. We are leading the observability category in CNCF. We are incubated in CNCF, but still we are in the landscape. These numbers are a little bit older. Currently, we are at 76 plus stars, 1,000 stars. And Netdata has 1.5 million downloads every single day. So all the agents have to update. So we count the number of downloads, of course, hundreds of millions of Docker Hub pulls too, etc. What makes Netdata unique? Easy. You just install it. You don't need to care about anything. It's true real time. AI is everywhere across the board. Even you can chat with it. You can troubleshoot with it. And the whole design, the distributed design of Netdata, provides extreme cost efficiency compared to any other observability you have seen. So we see from 50 to 90% cost reduction, and in many cases from 15 to 40, 50% infrastructure cost reduction. So the infrastructure itself can be optimized further to reduce cost. That's it. Thank you very much. This was my presentation. I hope you enjoyed it.